Welcome back, everybody. Okay, so just so you guys know, we had our quiz on Friday. We are doing section 5-4 today. We're doing section 5-4 today, and then we will review Tuesday, Wednesday, and then we will have our test over chapter 5, which is basically the quiz in one more section. We're going to have a chapter 5 test on Thursday. Chapter 5 test Thursday. Okay. So but just one more section, and honestly, this section is not that bad. It's a lot of the same stuff, just with a new test statistic. Okay. So the first thing that we're going to talk about, sampling distributions. Sampling distributions. Suppose this. Say I had every student at Lake High School, and I wanted to find their average grades. Okay, I wanted to find average grades. Maybe I wanted to find average math grade. We'll say that. I wanted to find average math grade of all the students at Lake High School. What would happen if I went into every single class and averaged their math grade? And then I went to Mr. Laverick's first period, average that math grade. Second period, average that math grade. Third period, average that math grade. And then I went to, and so on. And then I went to Mrs. Apple's, average. I'm taking samples, right? I'm basically taking cluster samples, right? I'm taking samples of their each individual means, right? I'm getting one score, one average for everybody in here, right? And then I take Mrs. Apple's first period, average it. Second period, average it. Think about those averages. In general terms, they should all be very similar, right? In general terms, if I take Mr. Laverick's Algebra 1 average, or math grade average, and then I took my second period average, and then I took my third period average, generally, I know there are some variations in terms of like honors classes and whatnot, but I'm talking generally, they should be about the same, right? So there shouldn't be that much variation. What that's called is taking a sampling distribution. That is called taking a sampling distribution. A sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. Now, I should have fixed my sample size. I should have said, okay, I'm going to walk into my first period class, I'm going to take 10 students, and then I kept that number at 10. Okay? Because you have to fix your sample size for this to be true. When samples of size n are repeatedly taken from a population. If the sample statistic is the sample mean, which is what I was talking about earlier, if the sample statistic is the sample mean, then the distribution is the sampling distribution of sample means. That is a long term. The sampling distribution. Whoa, that's not bad. The sampling distribution of sample means is just the name for what I was talking about. I know it's kind of got a lengthy name, but it's the sampling distribution, which basically means taking samples out of the entire population, sets of samples out of the entire population, and then taking each one of their means, the sampling distribution of sample means. Now, this is, I like this visual representation of it. This is what the book provided for us. I kind of like this because it's just a visual representation of what I was talking about. Say I've got a population with mean mu, right? And standard deviation sigma. Now think about, if I take more and more and more and more samples, right? If I take more and more samples, the population mean is going to start to look a lot like these sample means, right? The population mean is going to start to look a lot like the sample means, especially if I average those sample means, right? What would happen if I took X bar 1, X bar 2, X bar 3, X bar 4, X bar 5, and so on, and I average those values? That average value, the sampling distribution of sample means, if I take the mu of that, the more samples I take, the more that value turns into population mu. Now, why is that so important? Well, in my small example of students of Lake High School, I could possibly figure out the average math grade. We put it in it electronically. It's probably in some database somewhere along the way. But if I went something more broad and I said I wanted to find the average height of males in the U.S., that would be very hard to find, right? That would be extremely hard to find, especially if I wanted mu, right? If I wanted to guarantee population mean, yikes, no thank you. Don't want to do that. That's way too many people to take care of. So what I could do is start taking samples. And then find all of their means, then find the average of all of those means. And the more I do that, the closer and closer I can get to mu. The same thing is true for standard deviation as well. Finding a population standard deviation, way too difficult in some cases. Way too difficult in some cases. So what we can do is take the sampling distribution and find, okay, I'm going to take this sample, find its standard deviation. Take this sample, find its standard deviation. And if I repeat that process several times, well, then I can say that standard deviation is going to act like the population standard deviation, which we can, assume to be true. So, again, properties of sampling distributions of sample means. The mean of the sample means mu x bar. This is the notation for taking the average of the sample means. Mu x bar is equal to the population mean, mu. Okay? Mu x bar is the same as mu. That's what we just talked about. If we can take that mu x bar, if we can take x bar and find samples and samples and samples of means, and then I average those means, that's equivalent to mu. Mu x bar is mu. The standard deviation of the sample means, that's sigma x bar. Okay? It's written sigma x bar. Sorry for my sigmas always looking like sixes. But that's sigma x bar. That is the standard deviation. That's the notation for standard deviation of those sample means. Is equal to the population standard deviation divided by the square root of n. Now that's an interesting formula here. This is sigma x bar is equivalent to this true sigma of the population divided by the square root of n. Sometimes that's easy to find. Sometimes it's not. Sometimes that's helpful. Sometimes it's not. And I'll show you when it isn't. The standard deviation of sampling distribution of the sample means is called the standard error of the mean. That sigma x bar is basically like saying, how far does that average deviate away from the mean in terms of standard error? How much can I say, okay, we are confident in this statistic, but there's a standard error for that statistic where it can go above or below the mean, and it has to fall within that range. Okay, that's what's called the standard error. So let's take this example first. Let's take a small theoretical example. So say we write the values 3, 5, and 10 on little pieces of paper. Just 3 values, right? 3, 5, and 10. Say we had those 3 values. We put each one on a piece of paper, and we put them in a hat, and we're randomly selecting those values out of the hat. Now, oh my God, I have to go closer. Oh well. Okay. Say we had 3, 5, and 10 on a piece of paper. List all the possible samples of size n equal 2 and calculate the mean for each one. Now, this is a very small example where there's only 3 possibilities, and we're choosing 2 out of them. Here's what I mean by that. No pun intended. Mean. I've got 3, 5, and 10. Okay, so I could possibly choose a 3, then a 5, then a 3, then a 10. Right? Am I putting them back? List all the possible samples of size n equal 2 and calculate the mean for each. With replacement. Yep, I am putting them back. Okay, so I've got to include 3, 3 as well, right? Okay, so the other options are I could choose a 5, then a 3, a 5, then a 5, or a 5, then a 10. And lastly, I can start with 10. I can choose a 10, then a 3, a 10, then a 5, or a 10, then a 10. Those are all the possible samples, size 2. So like 3, 5, and 10 is all of my students of Lake High School. If I'm only going to choose sets of 10, Okay, that's my choosing set of 2 out of this. Okay, so let's find mu x bar. Oh, stop that. I need to move you down. Thank you. Okay, so this is my sample. Let's find x bars of each one of them. Okay, well, what is my mean here? My mean here is 3. My mean here is 4. My mean here 13. That's 6.5. My mean here is 8 divided by 4 is 2. Or sorry, 8 divided by 2 is 4. Is 5. 15 divided by 2 is 7.5. This one is 6.5. This one is 7.5. And this one is 10. Right? That's mu x bar. If I wanted to average those, it should be equivalent to mu. So here's my, I'm sorry, that's not mu x bar, that's just x bars. So now let's average those up. 3, 4, 6.5, 4, 5, 7.5, 6.5, 7.5, and 10. And how many do I have? I got 1, 2, 3, 4, 5, 6, 7, 8, 9 total possibilities. Mu x bar turned out to be 6. Mu x bar turned out to be 6. I did not need to do that. Why? Because mu x bar is the same as mu. What are my 3 possible values? 3, 5, and 10. What's the average of those things? 6. 5 plus 3 plus 10 is 18. Divided by 3 is 6. See, I didn't need to do that because mu x bar is essentially the same as mu. The reason I wanted to show you this is because that's essentially what you're doing when you're taking all those samples. You're taking samples of size 2 in this case out of 3 possible. But I want to show you that mu x bar always comes out to be mu if you take the samples of all the possible samples. And what we can say is, and which is the rest of this section, is that if that's not possible, you can say that if you average those together, it will eventually get to mu if you run enough samples. Now, let's. It said find the mean, variance, and standard deviation for the sample means. Use the population. Okay, so let's find sigma x bar. Okay, well, sigma x bar is sigma divided by the square root of n. Okay, well, the n in this case is 9, so square root of 9. See, what I don't want to do here, what would be way too much work in this case, is finding the standard deviation of all these red numbers. I don't want to do that. That's going to be way too long. I'm going to have to go to my formula sheet, figure out what standard deviation is again, and then run all those numbers. X minus x bar squared. X minus mu. X minus mu squared. X minus mu squared. X minus mu squared. And so on and so on. And then add them all up and run that value. But the nice thing here is that I've got this formula that if I can find the population standard deviation, all I need to do is divide that by the square root of n. Well, what's the population standard deviation? I've got 3, 5, and 10. That's pretty easy to calculate. It's x minus mu squared, and I want to sum all of that up. So in this case, I'm going to take 3 minus 6 squared plus 5 minus 6, in parentheses, come on now, plus 5 minus 6 squared plus 10 minus 6 squared. I'm going to add those all up, and I'm going to divide that by n. In this case, there's 3 of them. So I've got 8.6 repeating. That's my variance of 3, 5, and 10. And then when I square root that, this is the standard deviation of 3, 5, and 10. 2.94. 2.94. So the original sigma was 2.94. 2.94. Now, how does that help me? Well, now that I've found sigma, I don't have to run all those values. All I need to do is take 2.94 and I divide it by the square root of n. And so in this case, I take 2.94. I'm going to divide it by 3. So 0.98. 0.98. What is that telling me? That is telling me that these red numbers in this column deviate away from 6 by a factor of 0.98. That also tells me, well, in that case, I know that I have, because I've got this total population here, I know that, 68% of these values fall between 1 standard deviation away from the mean. So between 7 and 5, round, which is true. Okay. And I can tell, I can predict what's going to happen in the future as well. All right. Now, the central limit theorem says basically that if I don't take all of those little samples and get everybody included, that if I take enough of those samples, it will eventually lead me toward the mean. It will eventually lead me toward mu. If samples of size n, where n is greater than or equal to 30, and that's actually a number, then that's going to come up time and again. If samples of size n, where n is greater than or equal to 30, are drawn from any population with a mean mu and a standard deviation sigma, then the sampling distribution of sample means approximates a normal distribution. What's that saying? That's saying that if I take those x bars and plot them on a graph, it's normal. It's a normal distribution. The greater the sample size, the better approximation. The greater the sample size, the more confident I can be in saying that it approximates a normal distribution. If the population itself is normally distributed, I don't have to worry about the sample size. Okay? If the population itself is normally distributed, the sampling distribution is normally distributed anyway. So I don't really need to worry about n greater than or equal to 30 if I say that the initial population was already normally distributed. A couple other things. In either case, the sampling distribution of sample means has a mean equal to the population mean. That's what I was talking about. That x bar, if I take the mu of all those x bars, it will be equivalent to mu in the end, or get very close to it so that we can say it's the same. The sampling distribution of sample means has a variance equal to 1 over n times the variance of the population and standard deviation equal to the population standard deviation divided by the square root of n, which again, that sigma is equivalent to sigma divided by square root of n. Okay, that's that same formula. So what does that mean? What does that mean? How do we put this into practice here? Let's take a look. Residents of Lake Township have an average household income of $45,000. That actually is different. I actually looked this up last year because I was wondering if that was true. That's individual income, not household. So just double it for household income. A little less than that. With a standard deviation of 4,000. Random samples of 40 incomes are taken from the population. Find the mean and standard error of the mean of the sampling distribution. Okay, so what I want to do here is find the mean and standard error of the mean of the sampling distribution. I know that the average household income is $45,000, right? That's my mu. Right? I do need my notes. Hold on, please. I don't want to miswrite this. There they are. Perfect. Yeah, mu is 45,000 and sigma is 4,000. Random samples of 40 incomes are taken from the population. So n is equal to 40. Why is that piece of information important? Well, that piece of information is important for a couple of reasons. Well, one, I need it in my formula. And the other, because that tells me that it's greater than or equal to 30, which allows me to use the central limit theorem. See, I'm not told that the original population was normally distributed, so I have to know that n is greater than or equal to 30. Find the mean and standard error of the mean of the sampling distribution. So mu x bar. Yeah, mu x bar is going to be 45,000 as well, right? Because mu x bar is the same as mu for these values because mu x bar and mu are essentially the same when I have greater than or equal to 30. Now, sigma x bar we need to calculate. Remember, sigma x bar is equivalent to sigma divided by the square root of n. Now, in this case, think about it. If I run the averages, those averages should keep getting closer and closer together the bigger the sample size and the more times I take it. So that value should be much smaller than the true standard deviation. The true standard deviation is 4,000. But if I'm running averages, that standard deviation should shrink by a lot. So let's run that. That's 4,000 divided by the square root of 40. So 4,000 divided by the square root of 40 gets me 632.45. So sigma x bar again was 632.45. 632 rounding 46. Now, what is that telling me? That's the standard error of this statistic. That means that I can vary by a factor of $632 above and below 45,000. Right? That's my standard error. That's basically one standard distribution away from the mean. And that should cover a majority of the data, especially if it's normally distributed. And it does approach normal distribution because n is greater than or equal to 30. So the standard error, I know that I can range between 45,000, 632.46, and then I can subtract 632.46 from 45,000. And in between there, that's my standard error. They're in between there. Okay. Probability in the central limit theorem. So what we can do now is to say, okay, what's the probability that if I draw another sample, what's the probability that it's going to fall in that standard error range? Well, I can change that x bar into a z-score by taking my exact same formula that I had before. The value minus the mean divided by the standard error. So in this case, x minus mu over sigma. But the catch is mu is mu x bar. Sigma is sigma x bar. So we actually change it into this formula here. X bar minus mu divided by sigma over the square root of n. Because sigma x bar was sigma divided by the square root of n. So all we're doing is just taking that and inputting it right in there. Now, let's actually run that value. Let's do that. Let's run some numbers here. You randomly select 100 drivers ages 16 to 19. What is the probability that the mean number of accidents they have gotten into is between 1.1 and 1.4? Use mu as 1.2 and sigma as 0.7. We don't know where we got these statistics from, but we're given these statistics that mu is 1.2 and sigma is 0.7. What is that telling me? That tells me that the population mean, drivers age 16 to 19, the population mean is that they have gotten in 1.2 accidents. 1.2 accidents with a sigma of 0.7. So that means 0.7 above and 0.7 below is one standard deviation away from that mean. So what's the probability that if I select 100 kids, 16 to 19, that their mean falls between 1.1 and 1.4? Now, how do I know that this is normally distributed? Well, because my n is greater than or equal to 30. In this case, n is 100. N is 100. Okay, mu is 1.2. And sigma is 0.7. Now, I need to turn these into z-scores because I need to know what's the probability that it falls between 1.1 and 1.4, which is essentially the same thing that we did on our quiz, right? What's the probability that it falls between 1.1 and 1.4? Well, let's turn that 1.1 into a z-score. So in this case, z-score is going to be x, so 1.1, minus mu, 1.2, divided by, now here's the catch, it's not sigma, it's sigma divided by the square root of n, right? Sigma divided by the square root of n. So 0.7 divided by the square root of 100. Please catch that. That is not just the same z-score formula that we have been using. When I turn it into sample means, you've got to divide it by the square root of n as well. So in this case, this is 1.1 minus 1.2, so negative 0.1 divided by 0.7 divided by 10, square root of 100. So negative 1.43, double check that number, yep, negative 1.43. And then my next z-score is going to be for 1.4. 1.4 minus 1.2 divided by 0.7 divided by the square root of 100. So I take that 0.2 that I've got on top divided by 0.7 divided by the square root of 10. Or not square root of 10, just 10. So 2.86. 2.86. So now I just find the probability that it falls between there. Falls between 1.1 and 1.4. Well, I got to find negative 1.43 and 2.86. The big one, 2.86. If I go to my z-score table, I'm just going to cheat because I have it written down. 9979 for 2.86. For negative 1.43, I've got 0.764. So now the probability that it falls in between is going to be the difference between those. 0.9979 minus that's a 0.07. 0.0764. Minus 0.0764. So, come on now. 0.9979 minus 0.0764 is going to be 0.9215. So that's the probability that if I draw that 100-person sample, there's a 92.15% chance that mean falls between 1.1 and 1.4, which is a really slim margin. It's only 0.3 away. How is my probability so big? How is it 92%? Well, because that was a probability of mean, right? The probability of the average. I know that the average should be very close to mu. So if I know that I only want to go 0.1 below and 0.2 above, that's actually a big range comparatively for when I talk about values to actual mean values. Mean values should get a lot closer to the mean, where just a random value, well, that could be a little bit further spread apart. One more. Assume the height of males at LHS are normally distributed with mu 68 and sigma 3. If you random sample 8 male, wait. 8? Only 8? Why am I able to do this if it's only 8? Well, because I said my initial population is normally distributed. So if I say that the initial population is normally distributed, I don't have to worry about n has to be greater than or equal to 30. I can kind of bypass that. So mu is 68. Sigma is 3. I random sample 8. N is 8. Now, I want to know what the probability is between 67 and 68.2. Now, think about that. That's very close to my mean, right? That is extremely close to my mean. I'm picking 1 unit below and 1.2 units above. That's very close to my mean. I would say that my probability might be pretty low, but remember that I'm using means, not random values. So let's see what's going to happen. This is going to be, z is going to be 67 minus 68 divided by sigma divided by the square root of 8. Let's see what happens there. That's negative 1 divided by 3 divided by square root of 8. That gets me the z-score of negative 0.94. And then my other z-score is 68.2 minus 68 divided by sigma divided by the square root of 8. So 0.2 divided by 3 divided by the square root of 8, which gets me 0.19. Okay, now I've got to turn those z-scores into probabilities. The probability of negative 0.94 looks like it's 0.94. 0.1736. The probability of 0.19 is 0.5753. So all I need to do is subtract those two values and I get 0.4017. So what's that tell me? That tells me that it's a 40.17% chance that I fall in between those values. So it's a very strong probability that I am falling between there, even though that's a very slim margin to fall into. Why is that the case? Well, because I'm talking about means. I'm not talking about just a random value. I'm taking 8 people and sampling that, then taking its mean, then saying how close is it to mu. Okay. Now, the bigger I get with that sample, the closer it's going to get toward that mean, right? If I ran that same sample, if I said that same scenario with 100 people, well, then that would get a lot closer to that mean. I would say that variation is going to decrease a lot. Okay. All right, that's the notes for today. Here are the 5 problems for homework. I'm going to shut off the video.